Hello, all. Welcome back to next discussion on the quantum theory of scattering. So in the last lecture, we have discussed about the Bond series, and today we are going to discuss the first Bond approximation in the Bond series. So we can just go back to our Bond series. So the Bond series is the series expansion of the wave function, the total wave function, and this is the series expansion up to the second order. Okay, so second order bond series can be written as psi n of r mu upon 2 pi h bar square and so on. Okay, now what was the first bond approximation? That is what we are going to do today. Okay, so in the first bond approximation, the series can be truncated like this. Okay, the psi 1 is the first order approximation. So we are going to find the explicit form of this the first order approximation of the bond series. Okay, so this is the expression that we are going to deal today. Okay, let it be copied and can be pasted in our next session. Okay, so here we can paste it. Yes. Okay. Now, what is this psi in of r? The psi in of r and psi 0 are the same. Okay. So we know that in the zeroth order approximation, the psi 0 of r is same as psi in of r. And psi in of r will take the form e raised to I k0 dot r, because okay, so the your incident wave, we always take the plane wave as our incident wave. Okay, so then what would be the total wave function? So psi 1 of r, we can write e raised to I k0 dot r minus mu upon 2 pi h bar square integral e raised to I k modulus of r minus r prime divided by modulus of r minus r prime v of r prime, and the size 0 of r, I can write e raised to I k dot r prime, sorry, k0 dot r prime and d cube r prime. Okay, now we can simplify this in our next step. So e raised to I k0 dot r minus mu upon 2 pi h cross square, 2 pi h cross square integral. So here e raised to I k r upon r e raised to minus I k dot r prime and v of r prime e raised to I k0 dot r prime d cube r prime. Okay, so this term can be taken outside the integration. So therefore this becomes equal to e raised to I k0 dot r minus, better put plus here, plus e raised to I k dot r upon r minus mu upon 2 pi h cross square integral e raised to I k dot r prime v of r prime, then e raised to, okay, there is a minus sign here, e raised to I k0 dot r prime d cube r prime. Therefore, this become e raised to I k0 dot r plus e raised to I k dot r upon r minus mu upon 2 pi h cross square integral e raised to I delta k dot r prime v of r prime d cube r prime, where this delta k is given by k0 minus k. Okay, now if you look at this expression, so this is the wave function in the first order bond series. Now this wave function is a total wave function. Now the total wave function, the scattering problem, can be divided into two parts. One is the incident wave function plus the scattered wave function. And what is the form for the scattered wave function? The scattered wave function usually a spherical wave e raised to I k dot r by r, and there will be a scattering amplitude f of theta phi. So if you compare the total wave function with this, we can identify the form of the scattering amplitude. So by just comparing these two equations, so maybe equation number 1 and equation number 2. So just comparing equation number 1 and 2, we can identify our the structural form of scattering amplitude. So I can write the scattering amplitude f of theta phi, which is minus mu upon 2 pi h cut square integral e raised to I delta k dot r prime v of r prime d cube r prime. Now why this f of theta phi, the scattering amplitude, important? Because the scattering amplitude directly give the differential scattering cross section d sigma upon d omega. For elastic scattering, this d sigma by d omega is simply the modulus of f of theta phi square. Okay, so what would be our this scattering cross section? It would be given by mu square upon 4 pi square h cut raised to 4, then modulus of integral e raised to I delta k dot r prime u of r prime d cube r prime come out square. So next we can simplify this integration. So our integral is integral e raised to I delta k dot r prime v of r prime d cube r prime. So this can be written as integral. So there will be three integration. One is integration on r be from 0 to infinity, and integration over theta would be 0 to pi, integration over phi 0 to 2 pi. Okay, so this r theta pi. Okay, so this is a three-dimension 3D integration. So we can use any coordinate system as you like, and I am going to use the spherical coordinate system. Okay, and what are the integration variables? So it's v of r prime. Okay, this is r prime, v of r prime, then e raised to I delta k dot r prime, then it can be written as delta k mod delta k mod r prime cos theta. Then the integration variable would be r prime square sin theta dr prime d theta d phi. Okay, so therefore this integration, so integration from r prime from 0 to infinity, can write v of r prime first, then integral over theta, so theta 0 to pi e raised to I delta k r prime cos theta sin theta d theta, then integral 0 to 2 pi d phi, then again there would be an integration over r prime square dr prime. Okay, so this can be written as integral from r prime 0 to infinity r prime square v of r prime, and better I will write a dr prime at the beginning. So dr prime r prime square v of r prime, then integral this d phi, that would give 2 pi, can be taken outside. Then there will be this integration e raised to I delta k r prime cos theta sin theta d theta. So here better we can use another variable so that we can do it in next step. Integral 0 to pi e raised to I delta k r prime cos theta sin theta d theta. Okay, now we are going to put x for cos theta, then dx would be minus sin theta d theta. So if x is cos theta, then theta equal to 0 implies x equal to 1, theta equal to pi implies x equal to minus 1. Okay, so if you change this variable, then this integration would be 2 pi integral r prime from 0 to infinity dr prime r prime square v of r prime integral from 1 to minus 1 e raised to I delta k r prime x, and sin theta d theta would become minus dx. Okay, now what would be this integration? So this integration would be same as e raised to I delta k r prime x upon I delta k r prime. So it will be 2 pi integral 0 to infinity dr prime r prime square v of r prime e raised to I delta k r prime x divided by I delta k r prime, and the limit, there is already a minus sign here, so that minus sign can flip the limit. So instead of 1 to minus 1, I can put minus 1 to 1. Okay, so far so good. So it become 2 pi integral 0 to infinity dr prime r prime square v of r prime. So I delta k r prime. Okay, so one r prime can be cancelled. Okay, that can be do it in next step, and I delta k can be taken outside. So there is an r prime over here. So this become e raised to I delta k r prime minus e raised to minus I delta k r prime. Now what would be the result? E raised to I theta minus e raised to minus I theta. That would be 2I sin theta. So therefore this become 2 pi upon I delta k integral from 0 to infinity the r prime v of r prime 2I sin delta k r prime. So I think one I would cancel. So therefore finally it would be 4 pi upon delta k integral 0 to infinity r prime v of r prime sine of delta k r prime dr prime. So this is that integration. Okay, so we have just calculated this integration over there. Now it is possible to rewrite my delta k. So what is delta k? Actually, delta k is the magnitude of k0 minus k. Okay, so it will be root of k0 square plus k square minus 2 k k0 cos theta. Now for elastic scattering, okay, we are assuming the scattering is elastic. So elastic scattering means the modulus of k and k0 are same. So therefore this become 2 mod k0 square root of 2 mod k0 square 1 minus cos theta. Okay, so finally the result will be square root of 2 modulus of k0. Now 1 minus cos theta I can write 2 sine square theta by 2. So this become root 2 sine of theta by 2. And finally this is simply become 2 mod k0 sine of theta by 2. So hence our integration. So what is our integration? So integral e raised to I delta k dot r prime v of r prime d cube r prime. This can be written as 4 pi divided by delta k can be 2 modulus of k0 sine of angle theta upon 2, then integral from 0 to infinity r prime v of r prime sine of delta k r prime dr prime. Okay, so we have got we have simplified our integration, so the 1 2 can be cancelled obviously. Okay, so now we can write what is our final result for the differential scattering cross section d sigma by d omega, which is mu 0 by 4 pi square h cut raised to 4 mod square of this integral. So hence finally the differential scattering cross section in the first order Born approximation is given as d sigma upon e omega is equal to mu square by mu square upon 4 pi square h cut raised to 4 modulus of 2 pi divided by k0. K0 means the magnitude of k0 sine of theta by 2 integral 0 to infinity r prime v of r prime sine of delta k r prime dr prime square. Okay, so we have got a very convenient expression for the differential scattering cross section. So once you know the form of the interaction potential, we can calculate the differential scattering cross section at the different angles theta phi, so using this expression. Okay, So with this, we are stopping the discussion about the first bound approximation. So in the next class, our next discussion would be the validity of the first bound approximation. So thanks for watching. We'll see you in the next class.